Okay, let's get started. Awesome. Welcome to Office Hours. You should have your notebooks open, and you should also have the Adding Vectors Gizmo Simulation opened as well. Okay, but let's get started. I'm going to put my 20 minutes on the mark. Let's see what we went over. So we went over, okay, we went over two specific main things, one more than the other. But let's go over what we went over for the first part. We went over kinematics, right? And we know kinematics is just the study of motion. So kinematics equals the study of motion. Of motion. Study of motion, okay? So anything that goes down, sideways, that goes forward, that goes backwards, that's kinematics. And we need it. And some people were asking, why? Why is it so important? So I'm going to answer that question. Why is it important? I feel like I got a lot of questions on that. Why is it important? Well, first of all, it's important. Oh, I don't know what that was. That was supposed to be a plus sign. Anyway, it's important because it helps with direction. Like, for example, it helps out with a map. It helps with a GPS, like those GPS on your phones. The reason they can work are because of vectors and kinematics. It helps with the study of motion. So they're pretty helpful. But also, it helps with buildings, building schematics. Basically how a building looks, like the paper where they see like all the designs and how big it is and dimensions of it. It helps with that because it helps with also with magnitude. It helps with the dimensions and direction of the materials. So kinematics is really important with that because it helps like maps and GPS. The reason you can find your place pretty quickly are because of kinematics, how the motion is going, and then because of vectors, what direction you're going north, are you going south, are you going east, are you going west? And for building schematics. So if you have like a blueprint of a house, it actually tells you every single location and detail of that house. So you know how to build it. Okay. Give you a couple more seconds for that. Awesome. Let's move along. Okay. Now, we went over two main things. We went over scalar and we went over vectors. Right? And for scalar, it only has magnitude only. Magnitude only. Magnitude only, okay? For example, it has like 100 meters, 30 cups, 50 seconds, okay? It just has a magnitude. It has no direction. As opposed to vectors, vectors has both magnitude and direction. Okay, both magnitude and direction. So no longer is it 100 meters, but it's 100 meters maybe south. Right? It's no longer 50 seconds, but maybe it's 50 seconds ahead. And maybe it's not 30 cups, maybe it's 30 cups above. Okay? So vectors have directions and magnitudes. That's the only difference that they have, okay? A great way of writing them are like this. Scalar usually is just a variable by itself, but vectors have a variable with an arrow. Okay, that's a difference right there. With an arrow. So vectors, scalars just have the variable, while vectors have the variable with the arrow to tell you about direction, to signify direction. Okay. There's something else we also went over. Okay. Next one. Now, we also went over resulting vectors, right? So that's one of the new ones we went over, resulting vector. Resulting vector, right? And resulting vector is basically the sum of two or more vectors. Okay. Two or more vectors. And for the formula, for the ones who want to know about the formula, it's basically like V1 plus V2 plus V3, etc. And we need to put the arrows because that's how we know they are vectors, right? And it equals the resulting vector. The resulting vector. Oh no. There you go, resulting vector. So the formula is just adding all the vectors together and you will determine the resulting vector. Awesome, let's move forward. Pretty simple stuff so far, right? Now there's something that I want to go over for resulting vectors and vectors. For normal vectors, okay, and then for resulting vectors. And that's this. For normal vectors, it's always going to be the tip to tail. Okay? And in case you want to know what that means, in an arrow, if we have an arrow or a vector, whichever we want to call it, this part is the tip, and this part is the tail. Ooh, I do not like the way this is looking. Hold up. Let me make it a little bit skinnier. No. Tip. Tail. Okay? So for a normal vector, they're always going to be tip to tails. So that means they're always going to be like this. Okay? They're always going to be like this, the tip to tail, tip to tail, tip to tail, and tip to tail. Okay? Now for resulting vectors, when you're trying to find the resulting vector, that one's going to be a little bit different. That one's going to be the tips together and the tails together. Okay? So that basically means if you're trying to find the resultant vector of this, let's say, for example, you have this right here, and you have this right here, right there, right? If you want to find the resultant vector, you want to do the tails together, so right here, and then the tips together right there. So you see that? The tails are together and then tips are together. Boom, like that. Okay, let's move ahead to some examples. Examples are always good, right? Examples. Okay. Let's say blue. Oh. Let's say blue equals, let's say equals vectors, the normal vectors. Okay. And let's say a different color, let's say red equals the resultant vectors. Okay. Like that. So we have some examples like this. If we have, let's say, for example, the first example, we have it like this. An example, we have it like, oh. And an example, we have it like this. And then one more example, we have it like this. Right? For this one right here, we know the resulting vectors are from tip to tail. Sorry, the normal vectors are from tip to tail. But the resultant vector, we start at the tip, at the tails together, and then we move at the tip. Okay. Same thing here. We have normal vectors following a little path, tip to tail, and then tip. And then for resulting vectors, we start at the tail end and we move up onto the tip end. Okay. And the last one, we have tip to tail, tip to tail, tip to tail, and the tip. For the resulting vector, we start at the tail end and we move up until the tip. Let me make this a little bit thicker. There you go, like this. I can even make one more example, maybe just like this. Oh. Maybe an example like this. Like that. We got tip to tail, 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 and then tip. So for my resulting vector, I start at the tail and then I move to the tip. Pretty simple, right? Pretty simple. Awesome. Let's move forward. So at this time, you should just copy this down. This will be on your notes sections, or sorry, on your on Google Classroom on the async recordings. So I'll show you where that is again. So if you go, before we move on, if you go to my classes, to your Google Classroom, once it loads, and then you go to your physics classroom, go to the classwork, and then if you go to where it says all async recordings, you can see right here. Oh, I moved this to the wrong one. There you go. All async recordings, if you view it, it's going to be there. It's not there yet because I'm still recording it, obviously, but by the time you watch this, it'll be there. But all the recordings are right here, okay? Just FYI. Awesome. At this time, let's go on to the Gizmo simulation. I just want to show you some quick examples. So at this time, let's go to the Gizmo simulation. Recording. Okay, so you should be on your adding vectors simulation. Let's go over it. Remember, you go to Good Gizmos and then go to the adding vectors simulation. There's some things I want to do real quick. And those things are, for these final couple of minutes, are, first of all, I just want everyone to first pair these two vectors. We have two vectors. We have vector A and we have vector B, right? Vector A and vector B. I want you to pair them up from tip to tail. So however you do it, I just want you to pair them up from tip to tail. So the tip is this right here. And if you click on it, you can actually drag it and move the magnitude of it. And the tail is the little circle at the end. And that one actually moves the whole entire vector. But I want you to pair them up from tip to tail. So I have the tip of my A, and then I'm going to grab the tail of my B and just put them where the tip is right there. It can be whatever you want. It doesn't have to be exactly like mine. You can do it like this and then like this if you want to. Or you can do it like this and then like this. However you want to do it, it's up to you, okay? I'm going to do it like this. I want to make mine a little bit big. Okay, like this. Now, what I want you to do is determine where the resultant vector is going to be. So I know the resultant vector is going to be this missing piece right here, right? So we start at the tail, and then we reach at the tip. So if you go right here where it says show resultant, click on that, and it's going to show up a purple arrow. Obviously, the purple arrow is not paired up with the rest of the vectors. So let's drag this so it's paired up like this. Okay, so mine has a triangle now. Mine's a triangle now. So I have vector A connected to vector B, and then vector C, my resultant vector, has both the tail ends connected and both the tip ends connected. Okay, as you can see, you can't move your third vector, your vector C, you can't move it. You can't move the direction of it. Look at. If I try to reach the tip, you can't move it. The only thing you can move is the whole vector by itself. And that's because this is the official magnitude of the resultant vector. Now, that's pretty standard stuff, right? But let's see what happens when we move the tip of vector B. So grab the tip of vector B, and then just move it around. Remember, the green vector. Move the vector B around. As you can see, as you move the green vector, what happens to the resultant vector, the purple one? It also moves, right? Now, what happens if you move the blue vector around? Look at that. It also moves the purple one as well. So whichever vector you move, the resultant vector is going to follow. Now, obviously, this doesn't look accurate, right? But it will look accurate if you do from tip to tail. Look at that. So no matter where you move it, you can always pair it back together. You can always pair it back together if you rearrange them from tip to tail. See? It will always find its way back home. Look at that. See? So no matter how many times you move vector A and vector B, the resultant vector will always follow. Okay? It will always follow. All you gotta do is just rearrange them so you can complete the addition. Pretty cool, huh? I like it. Now that's the basic of this simulation. There's other stuff like show ruler, where you can actually determine how big the magnitude of those vectors are. But we won't go into detail for that just yet. I feel like right now it's not important. I just need you guys to know what they are specifically, okay? And then these ones just shows the angle. So if you pair up like this, it actually shows the angle of those two vectors. So in this case, it's 82.18 degrees, okay? But right now, those aren't that important. The only important parts are these vectors. You can show the parallelogram, show how it looks like parallel to each other, and you can actually show the sum computation. So when they're added together, what they're added to. So the x-axis 1 plus the x-axis of B, 7 equals 8. And the y-axis of A, which is -7, and the y-axis of B, which is 2, creates -5. So just in case you want to know the math side and the geometry side of it, okay? But that's pretty much it on that one. That's the only thing you need to know about the simulation. Just know that make sure you pair up the vectors accordingly. Make sure you always pair it on from tip to tail. And then when you're trying to find the resultant vector, you complete the puzzle, complete it. Boom, see? Like that, okay? Awesome, that's pretty much it for this recording. I hope you guys enjoyed it, and if you have any questions, you can always let me know. There's a question right now. It says, is there geometry in physics? There is geometry in physics, mostly trigonometry, which is a lot of triangles and a lot of right angles. So we'll get into that much deeper later on when it comes to projectiles. But there is geometry and trigonometry in physics. Pretty cool stuff, actually. But for the ones watching it, I sign you off. I hope you guys have a great rest of your day.